Okay, so now let's move on to the top of the distribution feeder circuit and see how all this load kind of bubbles up to form a net load on the circuit. And as an example of what one of these circuits could look like, this is something I talked about during the introduction. What we have here is we have a circuit where you have a substation, and then you have kind of like a main three-phase feeder that goes all the way down to all the different loads. And then we have all these different laterals that tap off of this main feeder, as well as a number of different loads that are actually connected up directly to this three-phase backbone right here. So you would maybe have like hundreds up to thousands of customers that would be connected up. And what we can do is we can take measurements. Typically the measurements at the substation in a top of the feeder circuit breaker relay, we can take measurements there. If we have downstream protective devices like reclosers, we can take measurements there. Sometimes we put special measurements out in the circuit, but at the very least, we'll have measurements at the top of the feeder. And so what we'd be concerned about is if we looked at the total amount of load in the circuit, we'd be concerned about, well, do I have any overloads? Am I loading something up too much where it might burn up? Or do I have issues with low voltage, especially at the ends of the circuit? All right, so this is why we would do the analysis that we do, all based on having a model for the net load in the circuit. As I mentioned before, we typically would look at summer peaks or we would look at winter peaks. And so in the class like ECE 586, where we talk about communications, this is typically what we do with these communication systems, is we pull back these measurements from the feeder. So for a residential feeder, this kind of shows what the profile would be looking like. This is the case where we're going to have a summer type of a profile. This is showing real power plus reactive power. So note, it kind of is the low point in the morning, and then it kind of rises up during the day until we hit our peak value. Reactive power kind of changes proportionally to the real power. What's interesting about this is you'll see that this reactive power goes negative, and typically when it associate that with the load, keep in mind though that this feeder also has capacitor banks that correspond to negative reactive load. And so what we're seeing is we're still seeing a cycling of the reactive power, but this curve's actually been shifted down due to the fact that I have capacitors also on the circuit. And what we're seeing is the top of the feeder, including capacitors as well. So if you go and calculate the power factor, if you take the real power and you take the reactive power, you see the power factor is pretty close to unity, which is what the utility would want to do. But the load power factor is probably going to be something like 92%, 94%, something like that. This shows an example of commercial load. As I mentioned before, it's kind of flat in the morning. It picks up during the day when people come in. It stays about flat, and it drops off in the evening hours, depending on when the business closes up. And then if you look at the reactive load, you'll see this reactive load kind of cycles. It kind of jumps up and down. This is because in this particular circuit, you have capacitor banks that are switching in and out. So as these capacitor banks switch in and out, it causes this reactive load to jump as well. What the utility is doing is trying to control the capacitor banks to keep this reactive load probably as close to zero as they can. In other words, they want to kind of keep the power factor close to unity. And then finally, industrial feeder load. This shows multiple days. It just kind of goes all over the place. You can see there's a typical profile for each day, basically where it has a similar sort of consumption. And then when you get to the weekends, it drops off quite a bit because they're in this case, not in production. So anyway, we'll get into this later on. We'll look at different load profiles later on in the project. You'll actually be looking at a load profile for a real circuit. So let's talk a little bit about utility rate structures, because this is what we sometimes want to adjust in order to incentivize the customers to use electricity better. May involve using less energy. It might involve using having lower peaks, right? And so when we talk about typical utility rate structures, there's different components. Sometimes these are referred to as tariffs. So what we're going to have is we're going to have an energy charge. This is something that's billed monthly. They pay so many cents per kilowatt hour. And sometimes there's no time of use characteristic to this. And so this could just be a fixed sort of a number. This relates to the utility's cost of generation or fuel. There's going to be a demand charge. This is normally dollars per kilowatt or dollars per kVA of the monthly peak demand, which talked about earlier. And so this would be done on a monthly by monthly basis. And so they look at the consumption over the last month and they pick out what would be this maximum demand. Again, this could be on a 60-minute interval or a half-hour interval, or could all be all the way down to 5 minutes. And what this is a mechanism to kind of induce the customer to minimize their peaks, give them some incentive to do that. If you're a residential user, you may see a fixed charge, might be a fixed monthly charge. This is a charge to connect. And then many utilities would have some type of time of use associated with this. And so this is where this kWh charge, or maybe this demand charge, would change depending on what time of day you're at or what time of year you're at. And we'll see this in a little bit, what this could look like. So if you're living in North Carolina next to NC State, and if you're living in an apartment or a house, then you're likely paying North Carolina Duke Energy residential service rate. The default would be to default to this rate, which is in rate schedule 65 in this case. This gets continuously updated. And so in a few more months, they might have an updated schedule. So this is a typical residential tariff. And what they do is they break the year into a July, October, and a November, June set of times for in terms of the charge. They have a basic connection charge per month, and then they have an energy charge. And you can see that in the wintertime, this would actually go down. And so kind of the idea behind something like this would maybe be, well, in the wintertime, if you need heat, heat's something you absolutely have to have, where maybe air conditioning, that's maybe a little bit more of a luxury. I mean, you could argue with that. But this typically also relates to is what's their cost of energy during these times as well. There's a renewable energy portfolio charge. And so this is what somebody would pay per month to pay for the state's renewable programs. And on top of that, you also have to pay a North Carolina sales tax. There's also a time of use schedule, and there's a couple different time of use schedules up here. I'm showing the one that has the demand charge associated with it. Again, they break this into a June through September and October through May set of charges. There's a kind of a fixed charge per month, a connection charge. And then there's also a demand charge. So what this does is it gives the customer some incentive to reduce their peak. And I've got this down as a 15-minute interval. So this is something that would come off of a smart meter. And then you have energy charges on here as well. And this energy charge depends on whether this is a peak time or this is an off-peak time. And the peak time versus the off-peak time would depend on the time of the day. And so if you're in the April through September time frame, then it goes 10 to 9 during the week. If you're in the October 1st through March 31st time frame, it goes either between 6 to 1 p.m. or 4 to 9 p.m. So again, what they're trying to do is they're trying to give customers an economic incentive for reducing peak at times that are also peaks for the utility. And so anyway, you'll have a different set of charges in the October through May timeframe, and we can actually do this type of a structure because smart meters would have the various sort of registers which are needed to capture all this particular sort of information.